Hi, I'm Tanmay Shukla. This is Lab 2 Projectile Motion Physics 2211. Introduction. The objective of this lab is to analyze and compare with a computational model the motion of an object that is thrown like a projectile, that is, it is thrown with an initial velocity in both the x and y directions. Tools used for Tracker, VPython, Excel, key physics principles. With Newton's second law, the rate of change of momentum of a body is directly proportional to the net force acting on the body. The air resistance also models a force that always points in the direction opposite to the motion of the object, and as a magnitude it's proportional to the square of the object speed. Drag force formula is therefore F equals negative bv square v hat, where b is a proportionality constant that I will determine based on experimental data, and v hat is a unit vector pointing in the direction of velocity. One formula is used with the position update formula and the velocity update formula. Experiment setup. The object uses a small paper clip. The camera setup is stationary and fixed sideways. The video is uploaded on Tracker for analysis, and a glow script was used for computational analysis. Assumptions. There was constant gravity, always acting downwards at 9.8 meters per second squared. Negligible wind effects, at least in the first computational model. Constant air resistance coefficient, that is the drag force proportional to the square of the object's speed and x opposite to its motion, that is the b value. Accurate tracking, that is the tracker actually puts out an accurate model of how it's tracked over time. This is the video from Tracker. The data from Tracker, the initial position of the object was at 0.0045, 0.02142, 0, which is approximately 0. That's the initial velocity. We found this initial velocity by subtracting the position of the object at t is equals to 0.033 as the first frame of the initial position in both the x and y direction to find the initial velocity in the x and y directions respectively. So we did it first in the x and then the y to find them both. This is the computational model initial conditions. They're both exactly the same except the one on the right differs with the value of b, which actually set as 0.1. Is the calculation loop in a computational model without drag. So you just loop over and you update the velocity of the ball and the position at each time and in each iteration, and you also plot the curves. There's a calculation loop in a computational model with drag. It's exact same thing. You update the velocity and position, but this time you get the force due to drag as well, and you same thing. You plot it in all the graphs in the x y. The observations on the left is a plot from the tracker data, and on the right is the actual tracker data. The computational model with drag, this is the plot position versus time. This is the plot for the computational model without drag for position versus time. This is the combined plot, so all the three plots of experimental data, the computational model without drag and the computational model with drag. As you can see, the experimental data is below both the other two graphs, which makes sense because of air resistance and other negligible effects. And computational model without drag is the farthest away from the actual data. The computational model with drag actually models the experimental data pretty well, although not completely accurately. Discussion follow-up questions. What does it mean? Do any of my models predict terminal velocity? And if the answer is no, a similar experiment could you design a find the terminal velocity of my object? So the model with drag predicts terminal velocity when air resistance, balance gravitational forces cause acceleration to stop. The gravity only model does not predict terminal velocity. To find terminal velocity experimentally, you have to drop the object from a much greater height and track its speed over time. Question number 2. Imagine if the object were initially thrown straight up with the same initial speed as in your experiment. Would the time this object takes to reach the ground be the same, longer, or shorter than the time taken on my original experiment? If thrown straight up, the object would take longer to reach the ground due to air resistance, slowing both the ascent and descent. Without drag, time up and down would be symmetrical, but with drag, the descent slows further. So some of the possible sources of error is obviously tracking inaccuracies, manual errors on marking points in tracker or even the software itself. Camera perspective distortion, maybe misalignment affecting position data. And there's air resistance estimation, is I may have used an inaccurate drag coefficient value. Timing errors, so frame rate limitations affecting time measurements. So that's it. This is Lab 2 of Physics 1, and I'm Tanmay. Thank you.